resilience, of course, to most of us civil engineers relates to elastic properties of a material. But in today's world scenario, the challenges that we face demand our systems and societies to be resilient. In other words, structural systems, as well as the construction industry at larger scale, need to exhibit an ability to bounce back from critical situations. This also applies to society in general, with the increasing incidence of natural and man-made disasters that the world faces today. Civil engineers definitely are at the core of developing solutions at different levels to cope up with the ever-changing global picture. Now, in this first session, we will feature talks that discuss issues related to resilience at various levels. The first talk by Professor Paolo Gardoni looks at how risk and resilience is analyzed. The second talk by Professor Venkatesh Kodur explores fire-damaged concrete structures. And the final talk in the session by Professor Ashwin Mahalingam discusses resilience at the urban level. Without further ado, allow me to present the first speaker in this session, Professor Paolo Gardoni from University of Illinois in Urbana-Champaign, where he is an excellence faculty scholar of civil and environmental engineering. In addition to being co-director of the Societal Risk and Hazard Mitigation Program and director of the MAE Center that focuses on creating a multi-hazard approach to engineering. Professor Gardoni has a rich academic background, having been trained at top institutions such as UC Berkeley. With over 140 refereed journal papers and 7 edited books, as well as nearly $30 million in research funds, he is a highly accomplished researcher. It gives me great pleasure to welcome Professor Gardoni for today's event. Professor Gardoni, over to you.
Well, thank you for the very kind introduction. I think you can hear me and you can see me. I'm also going to share my screen. Perfect. So thank you for inviting me to give a presentation at this workshop. The title of my presentation is An Introduction to Regional Risk and Resilience Analysis. As a background to the presentation, natural hazards can have devastating impacts on communities, and losses depend on the characteristics of the hazards as well as of the structures and infrastructure in the affected region. So today I will present a general roadmap for regional risk and resilience analysis. I will also introduce the concept of resilience, both as one of the most currently desirable characteristics of structures, infrastructure, and communities, as well as the necessary information for risk evaluation and decision-making. I will deliberately focus on the bigger picture, but I will also mention some specific engineering tools that we develop for promoting resilient infrastructure and communities. And finally, I will introduce a broader discussion of interdisciplinary considerations that should be accounted for in addressing current societal needs, including promoting social justice. This is the structure of my presentation, and I'll start by talking about physical damage or predicting the physical damage. There are 3 fundamental steps to predict physical damage. We need to model the hazards, we need to characterize the structures and infrastructure, and finally, we can predict the damage. So in terms of modeling the hazards, communities might be subject to multiple hazards, including floods, earthquakes, tornado, and fire, just to mention a few. And accurate hazard modeling requires accounting for the temporal aspect of the hazard. For example, for seismic hazards, sequences of main shocks and aftershocks all contribute to the overall damage. For weather-related hazards, climate change is impacting the likelihood of occurrence and magnitude of extreme events. So as to the seismic hazards, which will largely be the focus of my presentation, we develop a 2-step method to generate main shock, aftershock, ground motion sequences. First, using the branching aftershock sequence model, we generate main shock, aftershock sequences of earthquake characteristics. And then for each aftershock, we generate synthetic time histories using stochastic ground motion models generated using aftershock data. In addition, accurate hazard modeling also requires accounting for the spatial variability of the hazard. For example, in a region within 30 to 50 kilometers from the earthquake source or the near field, directivity effects might induce higher values of intensity measures along specific directions. The shape of the basin and the specific topography might result in amplification effects, and the characteristics of the soil and scattering phenomena might change the propagation path of the seismic waves. These factors limit the accuracy of the traditional ground motion prediction equations commonly used in seismic hazard analysis. And so we develop high-resolution, three-dimensional physics-based models that capture all of these aspects. To illustrate some of the concepts that I will present today, I'm going to use Shelby County, Tennessee. We've been considering a number of testbeds that allow us to test and verify different algorithms through calculations, experience, and engineering judgment. One of these testbeds is Shelby County, Tennessee, with a total population of about 1 million people that could be subject to earthquake scenarios originating from the New Madrid seismic zone. So in this example, we propagate in an hypothetical earthquake with magnitude 7.7 and hypocenter at the depth of 14 kilometers with two different levels of granularity. One is a high-resolution model in the near field and a low-resolution model in the far field. Other hazards where we model the propagation in space and time are wildfires and storm surge associated to tropical storms. Then we need to characterize the structures and infrastructure. So communities are composed by multiple layers of structures and infrastructure, including buildings, transportation network, electric power network, and the water network. Each network then consists of a number of different elements. And for example, the water network has elements that serve the following 5 key functions: supply, transmission, treatment, pumping, and storage of water. And these elements can be divided into linear elements like pipelines, tunnels, and canals, or point or nodal elements like tanks and reservoirs. For each region of interest, we need to define the footprint of each network. And the footprint of each network might exceed the footprint of the region of interest. Different networks might have different footprints, and the definition of the footprint of each network depends on 4 key factors: the type of information of interest, whether it's physical damage or loss of functionality, the existence of easily recognizable physical boundaries and the possibility to model the boundary conditions, the existence and location of strategic elements that need to be included, like generation nodes, and the modeling of the damage propagation among infrastructure systems. So for Shelby County, we consider the water network at the county level because it's a self-sufficient system. While for the electric power network, we had to consider the entire state of Tennessee in order to be able to run a power flow analysis. Once we define the footprint of a network, we also need to define its granularity, or if you want, the model resolution. So we define a tributary area as the area served by a single network node. And then by changing the tributary area, we can define networks with different levels of granularity. And in the limit, the most refined model considers each single parcel or house lot as the tributary area. The nodal value of the quantity of interest is then the spatial average over the tributary area. And in terms of modeling, different granularities affect our ability to describe the spatial variability of the impact over the area of interest. And I'll say more about this in the next slide. Also affects our ability to describe the changes in the network capacities and demands following a disrupting event. And finally, affects our ability to describe the recovery process, since skeletonized networks only include the main lines and not the smaller distribution lines. It is important to capture the spatial variability of the impact over the area of interest because certain population groups might be more impacted than others, or recover more slowly. And tributary areas that are too large would underestimate the actual societal impact. So the detailed network allows us to capture the variability within the larger tributary areas used for the skeletonized networks. So for example, we modeled the potable water network of Shelby County with two different levels of granularity. One is a skeletonized model of the network that I'm showing on the left, where we only consider the main lines. And the other one is a very detailed model of the network that I'm showing on the right, where we consider each line going to each individual home. Also, we modeled the electric power network with two different levels of granularity based on the area of interest. We developed a detailed model for the power network within Shelby County to be able to capture the variability of the impact within the county. And we developed a skeletonized model for the power network outside of Shelby County, which is sufficient to perform an accurate power flow analysis. And finally, we can predict the damage. For the point or nodal elements, we can use fragility curves. They provide a conditional probability of attaining or exceeding a prescribed performance level for a given intensity measure at the site. For the linear elements, we can use the repair rate curves. They provide the number of expected repairs per unit length of the linear element as a function of the intensity measure. So we develop physics-based fragility functions for the nodal elements. And to formulate the physics-based fragility functions, we first develop probabilistic capacity and demand models based on the fundamental rules of physics and mechanics, as well as information from the field and from the laboratory. And then using the probabilistic capacity and demand models, we can obtain fragility estimates by conducting a rigorous reliability analysis. In doing the reliability analysis, we can also account for the uncertainties in the model parameters. Now, I did not go into the details of the math. I only gave you an overview. I just want to point out 5 important advantages of the physics-based fragilities that we develop compared to the fragilities that you can otherwise find in the literature. First, the fragility functions are parametric. So once the capacity and the demand models have been calibrated, they can be used to assess the fragility of other elements with characteristics that fall within the range of the data using the calibration. The modeling can be done at a structural component level, which can take advantage of the experimental data often available for structural components, but not for the full system. The fragility estimates are obtained by doing a rigorous reliability analysis rather than by making simplifying assumptions on the shape of the fragility functions, such as assuming a log normal cumulative distribution function. The parametric formulation allows us to easily incorporate the effects of deterioration and the information from non-destructive testing and structural health monitoring. And finally, the estimates account for the relevant uncertainties, including the statistical uncertainty that comes from the scarcity of the data used for the model calibration, as well as the model uncertainty that comes from the simplification in the mathematical models. We're currently using this formulation to develop physics-based repair rate curves that are intended to replace the purely empirical repair rate curves that can be found in the literature. So going back to the example of Shelby County, we use the earthquake intensity measures and the fragility functions to estimate the damage of individual buildings in the region. We're looking at residential buildings, what I'm showing on the left, commercial buildings that I'm showing in the center, and the industrial building that I'm showing on the right. The top row shows the estimates of the damage using the traditional attenuation relationships. The second row shows the estimates of the damage using the more advanced three-dimensional physics-based model. And we can observe localized high damage due to the hazard amplification in certain areas, which is not captured by the traditional attenuation relationships. Also, on average, there is less structural damage in the residential buildings, but more structural damage in the industrial building given their specific location. Then we can talk about dependencies. Physical infrastructure often depend on each other, and such dependencies might indirectly affect a network capacity. Buildings, for example, need the service provided by the water and power network. The water network depends on the power network because it needs the power at the pumping station and control systems. As a result, even if a network has no physical damage, there could be a loss or reduction of functionality of such network because of the physical damage and the corresponding loss of functionality of the supporting network. And so we need to translate the physical damage into a loss or reduction in functionality and then propagate such loss or reduction across all dependent networks. So considering the example of Shelby County, we first estimated the impact of the earthquake on the power network capacity. In this case, we estimated a complete power blackout for Shelby County. We then estimated the impact of the earthquake on the water network capacity. First, we found considering the dependency of the water network on the electric power network, and then also considering the dependency on the electric power network. And we see that accounting for the dependency of the water network on the power network significantly reduces the ability of the water network to deliver water. The service provided by the supporting infrastructure also affects the building functionality. For example, we estimated the probability that each commercial building is not functional considering structural damage as well as access to water and power. So considering only the structural damage, we significantly underestimate the lack of functionality of buildings. In this example, due to the likely power blackout in Shelby County, in the immediate aftermath of the earthquake, the most likely functionality states of the buildings is non-functional. But not only the capacity, also the demand can be affected by dependencies. For example, the building damage can lead to people dislocation or business interruption that affect the post-event water network demand. So the updated network capacity and demand can then be used together in a flow-based network analysis to assess the functionality and reliability of the network. Considering Shelby County, we studied the effect on the water demand of people dislocation due to a seismic event. And we see that thanks to the reduction in the water demand, the water network actually performs better than if we did not consider people dislocation. And finally, we can model the business interruption, which is a disruption of the normal operations of a firm. So we studied the effects of a number of contributing factors on the likelihood of business interruption. And as an example, we predicted the business interruption of an hypothetical shipping company in Shelby County. To predict the probability of business interruption, we consider structural damage as well as lack of water and power. And we see that the loss of service from the supporting infrastructure can have a very significant impact on the probability of business interruption. After talking about the immediate impact, we can also look at the recovery, the resilience. So current design approaches are pushing toward options that are resilient under different exposure conditions. We want to increase the robustness, or if you want, the residual functionality immediately after an event. And this is related to the fragility estimates and the repair rates that I discussed earlier. But also we want to accelerate the recovery process, which is related to the recovery curves, which I will discuss next. The actual shape of a recovery curve is influenced by different factors, including the type and level of damage, availability of resources required for the repair, and environmental conditions and preparedness. Functions with different shapes have been used to model the recovery curves, where the choice of the function is often based on a qualitative description of the situation. To model the recovery process in a more rigorous way, we develop a stochastic formulation that accounts for the actual work progress that need to take place for the recovery. And then, as the individual component recover, the entire network functionality also recovers. And so we model the recovery of the power network considering considering the actual priorities in a real post-disaster recovery. And we found that after about 32 hours of repair work, all critical components have recovered. Similarly, we modeled the recovery of the water network, and we found in about 21 days of repair work, most of the water network has recovered too. Finally, considering the example of the shipping company, we estimated the recovery of the business operations. And we see that the building recovery is expected to take the most time. And also, since the building recovery typically begins only after the recovery of the water and power network, we need to add these times to the overall recovery. And in addition, building recovery requires the availability of the workforce, material, access to the site, which require the larger portions of the water, power, and transportation networks also recover. And as a result, the estimated building recovery times shown here are only lower bounds of the actual recovery time. To estimate the actual recovery time, we need to consider the recovery of the entire servicing area and of all supporting infrastructure. So a few concluding remarks. An accurate regional risk and resilience analysis requires capturing the spatial variability of the hazard and in the condition of the structures and infrastructure. Requires selecting the proper model granularity, since certain population groups might be more impacted than others or recover more slowly, and models that are too coarse would likely underestimate the actual societal impact. Requires modeling the dependencies and interdependencies among networks to capture the loss or reduction in functionality of the supporting critical infrastructure in addition to the structural damage. Requires accounting for the aging and deterioration of structures and infrastructure, which can have a significant impact on the vulnerability of the built environment. This is something I did not include in my presentation because of the limited time. And finally, it requires modeling the resilience of the structures and infrastructure to estimate the duration of the impact. A preliminary study on Shelby County, Tennessee, has shown that using traditional attenuation relationships might misrepresent the seismic hazard, leading to incorrect estimate of the structural damage and the loss of functionality. Also, the loss of functionality of the supporting water and power network tends to increase the probability that residential, commercial, and industrial buildings are not operational in the aftermath of a catastrophic event. It also tends to increase the duration of the recovery time and business interruptions. And finally, an accurate prediction of the duration of business interruption requires considering the recovery time not only of the building facilities, but also of the supporting infrastructure and of the entire servicing area. So if any of the things I've discussed today are of interest to you, I want to point you to the journal Sustainable and Resilience Infrastructure. This is an international journal that focuses on sustainable development of resilient communities. And finally, I want to bring to your attention the Radler Handbook of Sustainable and Resilience Infrastructure that captures many of the things that I present today. Thank you.
Thank you very much, Professor Gardoni. That was indeed enlightening. Typically, when we think of earthquakes, we only look at structural damage. We don't think of these connected hazards which can affect the life of communities in the region as a whole. We do have a few questions raised for this session. The first question to you is, can we generalize that lower demand increases the resilience of a system?
I don't know whether we can make it a 100. I'm sure we can find some cases where this is not true, but if you think of trying to balance the capacity or the service provided by the infrastructure and what the infrastructure is asked to take, then a reduction in the demand, of course, helps, because the infrastructure is asked to provide a less service. And so we have seen this for power, we've seen this for water. I would say it's relatively general, but it is possible that one can find some unusual case. I wouldn't make it 100%, but that's what we have found in general, yes.
Now, you talked about various levels of analysis, starting from the state to the county to the city to the region. Now, would this level of detail that you study for different types of disasters, would it be different for different types of disasters, or would you have the same approach, for example, in the case of a flood as in the case of an earthquake, and so on?
So the way we have been approaching the problem is different from some of the work that has been done in the past, that is more of a 3,000 feet, if you want, approach, more at the where there is an average value, for example, at the county level. The way we've been doing it, we've been calling a ground-up approach, where we're basically modeling all the details. We have every individual building, we have every line, we have for the water and for the power. The moment you have all these details, you cannot have something that is even more granular, if you want. And the only issue would be computational, but we found that with the current computational power, this is not necessarily a big issue. So largely, this ground-up approach can be used for any of the hazards that we consider, which are earthquake, storm surge, wildfires. It really depends also on what is the desired outcome that you want. If you want to have information at the individual building or the individual structure, then inevitably to have something accurate, you have to model them. If you are interested in an average over the region, then one could consider a higher granularity. You lose a lot because you lose the spatial variability, which was one of the things I was saying is important, even to look at the differential impact. Because if you have something that is at a higher level and you have an average over that region, then all you can say that everybody on average has that impact. But that's not true. Some might be impacted more than others. And so that's why I'm advocating for a higher granularity than an overall average over the region. But if you are only interested in the average, which could be the case for certain decisions, then you could have a higher level of granularity, which would be computationally more efficient.
Thank you. The next question is, can you explain the in brief, the necessary steps for resilience analysis of a typical coastal city which sometimes get hit by cyclones? For example, we have several hurricanes in the US and cyclones in India. In such cases, what would be the steps involved in resilience analysis?
Pretty much the same thing that I presented here. In fact, and I don't know if I don't want to revolutionize the logistics, but I can re-show my screen if you want. One of the hazards that we consider is the storm surge due to hurricanes. And so we have been analyzing Miami, for example, exactly for a storm surge. And the way we approach the problem is exactly the same. So we have the model for the different buildings, for the power, for the water, for the wastewater, for the storm water, even beyond the one I showed here. And then we need to model the hazard, which in this case would be different. It would be, for example, the inundation. But again, we need to have a time component, and we need to have the spatial variability. So the process, I explain it using an earthquake, but it's pretty much the same, even if the overall process, if you want, the procedure is the same. What would change are the specific models that we use for the hazard and for the fragilities.
Okay, thanks. We have a question on how we can compute the aging of the structure. I presume this is related to in a disaster or in an event.
Yes, in fact, I have a longer version of this presentation where I go into the details of the aging and deterioration as well. if inside the fragilities, which I just put out there without going to the details of the math, but the fragilities are functions of what we call state variables, the geometry and material property of the structure. And so then we can use models that give us the deterioration and the change in time of these state variables. And so we can obtain time-varying fragilities and time-varying repair rates. And then we can use them in this analysis. So if we have a structure that is 100 years old, the probability of failure or probability of exceeding a certain performance level will be in general higher than for a brand new structure. And we can do this very nicely by incorporating these deterioration models inside the fragility and inside the repair rates. We have done that, and the other nice thing is that we can incorporate information from structural health monitoring and non-destructive testing, because they would all go in the definition of the state variables that go into the fragility.
This next question is quite similar to the one which was raised earlier, whether the resilience modeling of different types of disasters, is it different or can they have common parameters? But I think you've already answered that. The only one different aspect about that question that was raised now was the current pandemic, the COVID pandemic. So again, from that point of view, do you have any other perspectives on that question with respect to the current pandemic that we face?
So we have been thinking, so these are all great questions, by the way. For all the previous one, I had a clear answer because we have done it. For this one here, all I can say is that we have been thinking if we can use some of these formulations or a general probabilistic framework in the context of a pandemic. And we found that there is expert knowledge that we don't have in terms of epidemiology, for example. But I do believe that one could couple this work with working in collaboration with somebody who is an expert in epidemiology, for example, and this could help bring some of the mathematical rigor in a different field. The other aspect that is related is, I was talking about the dislocation here. That means people, they don't have access to their home and they need to go somewhere else. Okay. And often they move to schools, they move to the basketball arena, they move to some buildings, maybe inside the city, sometime outside of the city, but they live in very close quarters. And this is something that would be problematic at the time of the pandemic. So if a hurricane, if a cyclone, if a typhoon, or a natural hazard has to happen now, the population dislocation would be much more problematic. And I think this would be a nice opportunity to couple some of the work that we've done that is primarily related to natural hazards and the issue of a pandemic.
Great. Just one final question to the Gardoni. What impact will it have if spatial variability is not captured for regional risk and resilience analysis?
If it's not captured, there are different places where the spatial variability plays a role. One is the spatial variability of the hazard. And I think this is very important. This is not something we can give up, because you need to be able to capture the fact that certain areas might have a higher intensity measure of the hazard than other ones. So that spatial variability, I think, is key. There is a spatial variability in the deterioration conditions. If it's more of a coastal breach, for example, might be exposed to higher deterioration than one that is inland. I think this is also important. We have not seen this to play as much of a role as the variability in the hazard, but I think it's also important. The third piece, and maybe that's what the question was more related to, is the spatial variability in the impact. And if you don't have it, what you lose, that's what I was saying earlier, what you lose is the variability across the region and of the impact, and so you only have an average. but the average is problematic because those that are more impacted than the average are really worse off, and we need to be able to capture that. And in fact, much of if we use this type of analysis for the purpose of decision making, some of the decisions are really driven by the larger impacts, not for the average. And so if we look at the average and we ignore the peak values or the extreme values within the region, we wouldn't be making the right decisions.
Okay, thank you, Professor Gardoni. That was indeed enlightening. Thank you for patiently answering all those questions. I'm sure that the audience has been enriched by this experience. I'd also like to thank you for being one of the former guides and advisors of my colleague, Professor Radhakrishna Pillai. We are indeed very happy to have you here. I'm sure that he's thrilled that you have been able to make this presentation. So thank you very much.
It was my pleasure to be his co-advisor.
Thank you. Thank you so much.
Thank you for having me.